As Jos mentioned, I am James, and today I'm going to be talking to you about long-term glass behaviour testing. It's a bit of a clunky title, so let me shorten that for you to simply LGBT+. So, over the course of the next 10 to 15 minutes, I'm going to tell you a little bit about myself, before I tell you about why we as engineers and scientists should care about LGBT issues. Then I'm going to tell you about how we undertake long-term glass behaviour testing, LGBT, before I tell you a bit about some LGBT work that I have already done. Might be time for a conclusion at the end as well. So starting off with a bit about me, so for the second time, my name is James Mansfield. So I'm currently in my second year of a PhD here at the University of Sheffield at the Department of Material Science and Engineering. I identify as the G in LGBT, and originally I am from a tiny little village in North Northumberland. No one will have heard of it, so I won't tell you where it is. After getting bored of living in this tiny little village, I then moved to Glasgow University to do a bachelor's in Earth Sciences, or Geology, before I moved to University College London to do a master's in Geophysical Hazards, which is all of the cool stuff in geology like the volcanoes, earthquakes and tsunamis. I then came here to Sheffield a couple of years ago to start my PhD. That's enough about me. So fundamentally, I believe that all of us material scientists and engineers should care about long-term glass behaviour testing, because this could help us solve our problem concerning nuclear waste. Now, I appreciate this might sound a bit far-fetched to you, so let me tell you more about this nuclear waste problem we have. Starting off by telling you a bit about this nuclear waste itself. So the UK's nuclear waste typically forms a flowing liquid comprised of all of these elements here. Now, the problem is that quite a lot of these elements are radioactive, so if they get out into nature, it can cause quite a lot of harm. Furthermore, some of them are also toxic. So the combined radiotoxicity of this waste means that we need to keep it away from people and nature for at least the next 100,000 years or so, or hopefully indefinitely, if we can manage that. Fantastic. So how do we plan to do this? Well, the current plan is called vitrification and geological disposal. Let me go through this for you. So we're going to take our liquid waste and we're going to solidify this into a solid block of glass in a process known as vitrification. We're then going to whack this glass into a steel canister before surrounding this steel canister in a layer of clay and burying this hundreds of metres below the surface. Now this all sounds quite cool, but where's the problem with it? Well, the problem comes when we have to prove to you, the public and the politicians that this is safe. In order to do this, we consider the worst case scenario, and if this is kinda okay, then we can be confident that it's safe. So this worst case scenario I'm talking about consists of water getting all the way down to the place where we're going to put our waste, hundreds of metres below the surface. This water would then somehow, God only knows how, penetrate the clay layer and then get into our steel canister, perhaps because the canister had cracked or something else. Anyway, this water would then contact our glass and cause the glass to dissolve, leaching out the radioactive stuff. So what we're left with is a load of radioactive water, and then potentially, in our worst case scenario, this water could make its way all the way back up to the surface to end up in Mrs. Mulch's flower bed or in her cup of tea in the morning or something like that. So that's our worst case scenario. Now, key to that is the long-term behaviour of our glass. If our glass doesn't dissolve much at all, then there won't be any source of this radioactivity, so we can be fairly sure that it's a safe option. That's why LGBT is crucial, because if we can prove that our glass doesn't dissolve, it has a fairly good long-term behaviour, then we can be confident that our plan for nuclear waste disposal is safe. So, given that LGBT research is so important, how can we conduct it? Well, let me explain this by first introducing you to another problem. Glass dissolution, in most cases, is slow. That's why you're all sat here today drinking out of glasses, because we know that short-term, glass doesn't react much with water at all. Similarly, we have these Egyptian glasses that prove that long-term, most glasses are fairly stable as well. But this is a problem for us material scientists because we need to know how glass dissolves. We need to determine the mechanisms. So in order to do this, we speed it up. So let me explain to you how we do this using an analogy. So if you're at home or out at the shop and you're trying to dissolve in sugar into your tea, this is particularly difficult if you're trying to do it in an iced tea because the tea is cold. So, one method we use as material scientists is to heat up the water. This effectively speeds up the rate of reaction and makes the dissolution a lot faster. It's also well known that it's more difficult or takes longer to dissolve a solid sugar cube than it does powdered sugar. That's because in the case of powdered sugar, there's a greater amount of the sugar particle in contact with the water, a higher surface area to volume ratio. That's why we often powder and heat our glass samples in order to get them to dissolve in water. However, there's a problem with this method as well, in that the conditions in which we're altering these glasses are not representative of those in our geological disposal scenario. For example, our glass isn't going to be altering as a powder, and the temperatures aren't going to be massively hot. So in order to overcome this problem, we can instead look at old glasses that have been altering for ages. The benefit of these is they have been altering under similar conditions to the glasses where we're going to put our nuclear waste. However, the problem with these is that the composition of these glasses is not similar at all to the composition of the glass where we're going to put our nuclear waste. So we know from lab experiments that we're most likely to put our nuclear waste in a borosilicate glass. That's a glass that contains a lot of boron and is quite similar to your Pyrex dishes at home. But the problem is that there isn't much boron in nature, so not many of our geological or archaeological glasses contain a lot of boron. So, the ideal solution to all of this is to do as much LGBT research as possible. We need to use a range of long-term glass behaviour testing methods in order to overcome the problems associated with each. So, given this, let me tell you a bit about the studies I have done concerning long-term glass behaviour testing. So I have done this hot powder testing type stuff in a project where I aim to investigate the effect of radioactive decay of the waste on the glass's durability, so the glass's propensity to dissolve. So in this, I made a decayed and an undecayed glass. When I say I made a decayed glass, my university wouldn't let me play about with a load of radioactive waste, so I had to simulate this decay. In order to do this, I changed the composition of my glass subtly, and I also changed the speed with which I cooled my glass, because previous authors have found that decayed glass behaves quite similarly to glass that has been cooled quickly. That's why in the picture in the middle here, you can see me cooling my glass by dropping it into a bucket of ice and cooling it with a fan. It's quite basic, but it was the best we could come up with. So, after I had made my blocks of glass, one of which I think I have here for you to have a look at. There you go, there's some glass. Have fun. Just don't lick it. Otherwise you might become radioactive. No, you won't.
Do I get any superpowers?
No, you might die now. So after I had made my beautiful blocks of glass, I had to powder them. So in order to do this, I wax it with a mallet over and over and over again till my arms fell off. Then I passed it through some sieves just to make sure I had all the same grain size. Then I put this into an oven in a tiny little pot, one of which I may well have. Or not. I mean, it's just a pot, basically. Oh, there we go. There's a pot. So I put my powdered glass into a pot and then put this in the oven to dissolve. So in terms of the results of this, well, I came back after a certain amount of days and went to check the solution in these pots to see how many of the elements from the glass had entered the solution, so how quickly our glass was dissolving. What I found was that our decayed glass and our undecayed glass dissolved at a similar rate. So therefore, decay doesn't have much of an effect on the durability of our glass at all. So that was quite cool. But then I also went on to look at some archaeological glasses as well. but they're nothing like those Egyptian glasses I showed you a minute ago. Instead, I studied glasses from hill forts. So hill forts are basically fortifications like these that were built on top of hills, obviously. These were built out of local cobbles or stones that were just kind of jumbled together. However, the cool thing about these is that the local people often used to set them on fire. We're not quite sure why they did this. It could have been their enemies in order to destroy their opponent, or it could have been the people living there in order to strengthen their walls. It could have also been an accident just because they were silly. But anyway, regardless of why these fires were started, they caused some of the wall rocks to melt to form a lava. This lava then cooled super quickly to give us a glass. So what we're left with today is walls like this made out of glass. These hill forts are known as vitrified hill forts because they are vitreous, they are glass. Anyway, the particular hill fort that I was looking at is up in Scotland. It's on the western flank of Ben Nevis, which is ideal for us because, as we all know, Scotland is bloody wet. So this glass has been sat in the pouring rain for about the past 2,500 years. So we can be fairly hopeful that it's dissolved a little bit, at least. At least it's the ideal place to look for dissolution of glass. So what did I find? Well, here are some images. These are tiny little pits in the surface of my glass that we think formed as the water preferentially attacked certain weak points in it. But anyway, these pits, as well as some entire surfaces on my glass, are covered by this beautiful iridescent layer. It is quite in keeping with the LGBT rainbow flag thing, so I quite like them. Anyway, these layers we hypothesised formed as the solution in which the glass was dissolving became so jam-packed with elements that these elements simply fell out of the solution to precipitate as a layer. So, these we think evidence dissolution, and I think they're quite cool. But they're not quite as cool as these amazing pictures. Now these, I'm showing you them just because I like the pictures, because I'm disappointed to tell you, they have absolutely nothing to do with glass dissolution at all. Instead, they're just due to the way we mounted our sample. So these cool patterns are just layers of glue, which I was quite sad about when I discovered it, but I like the pictures anyway. So, my conclusion. I believe that LGBT activities can help us solve our nuclear waste problem because they can help us determine whether our current method for nuclear waste disposal is safe. However, long-term glass behaviour testing requires a lot of novel techniques. So we need to, for example, heat our powdered samples, or we can look at archaeological samples as well. My own long-term glass behaviour testing studies have implied that decay does not massively affect our glass's durability, and I hope to continue looking at my vitrified hill fort samples in order to determine what they can teach us about glass dissolution. Thank you ever so much for listening. I've been James. If you have any more questions, feel free to email me or follow me on Twitter. Thank you.